So here is a question that I'm going to be asking in class, and you'll be able to answer with your clickers. There's a series of exercises we'll be doing with this one. So now we've talked about what happens when there's more than one interaction on a particular object. So the system is very simple. It's one object. There are many interactions on it. It's the vector sum of the interactions that tells you how the object changes its momentum. But the definition of the system, that is something that is really up to you. The universe doesn't say what a system is. So we have some freedom here when we choose to approach a problem as to what the system is. And here I've made a system that has got two pieces of matter in it. So the surroundings are everything else. These two objects are interacting. I see M1 with V1 and M2 with V2, so I know the momenta of both of these two objects. So I know what the momentum of the system is. The momentum of the system is just the vector sum of the momenta of the pieces. So object number 1 has a momentum. That comes from this M1 and V1. Object number 2 has a momentum. P2, M2, V2. Now we know from our momentum principle that if we've got the net force, the net interaction with the surroundings is 0, then the momentum of the system cannot change. The only thing that can change the momentum of the system is an interaction from the surroundings. There is no interaction from the surroundings, so here's the momentum update form. The final version of the system momentum has got to be equal to the initial version of the system momentum. It cannot have changed. So I know that the momentum of the system does not change. That's for sure. That's something you can go to the momentum principle. You can always go to a fundamental idea and get a right statement. So I know the total momentum of the system can't change, but can P1 change? P1 is just the momentum of object 1 here. So there's P1. Can P1 change? And that's something that you'll have to be thinking about when we get into it. Now, what would it look like? Let's think about what happens in these two systems. Let me define different systems. So here is, I'm going to define a system which is got M1 in it, and it's got its V1 the same way. Your choice of system does not affect what actually is observed by anybody. Your choice of system helps you solve problems, but it can't change what's going to happen in the universe. So here's M2. Let me make another sketch there. There's M2, and it's got some V2. It's now the surroundings for the system that is M1. Here's my system. And my system boundary is there. So now I'm asking, if M2 is a part of the surroundings, can the momentum of my system change? And if the momentum of my system can change, then yes is what you should be clicking on that when we get to that in class. Well, see here, you're just asking, can the momentum of an object change? And sure it can. It doesn't have to. If it interacts with M2, then it's going to change. So here I've made, now the surroundings are free to interact with M1. So let's find out what that interaction is. The momentum principle will tell me exactly if P1 changes, I would have P1 final. That's the final momentum of this object. It's equal to its initial momentum, which I've drawn there, P1 initial, plus the interaction from object number 2 times delta t, however long that interaction lasts. So if there's an interaction, if M2 interacts with M1, M1's momentum will change. That's what the momentum principle says. And that's what we've written there. So this is if object 1 is the system. Let me now make object 2 the system, the red system. So now object number 1 is the surroundings. What I would have is, let me do this in red because it's the red system, the momentum of object number 2 in the final state. Because object number 2 is now going to interact with object number 1. Object number 1 is the surroundings. It interacts with object number 2. So momentum 2 final is equal to the initial value of object number 2 plus the interaction from number 1. And then times delta t, however long that interaction lasts. The thing that's the same, so these are two different statements. The momentum principle tells us two different things because we made every choice a system tells us something. the delta t is exactly the same because it's the same interaction, right? You can't have the Humvee and the Mini interact for different amounts of time. Those bumpers are touching for the same amount of time. So the delta t's are the same. And if I make a blue choice, the system, I'm back to my initial statement here that P1 final plus P2 final, that's the final momentum of the system, right? That's this, is equal to the initial momentum of the system, P1 initial plus P2 initial plus the force from the overall surroundings times delta t, but that's 0 because there is no interaction apart from what M1 and M2 are doing. That's the case that we're considering here. So these three statements together are going to tell us something about these interactions, about the force from 2 and the force from 1. And it's something you've heard before. You've heard this stated as a statement of politics or a statement of how groups work. For every action, there's an equal and opposite reaction. So it's also something that you've heard maybe called the law of conservation of linear momentum, but that is a special case of these three separate analysis in three separate applications of the momentum principle. So let's just add. Let me call this one equation number 1 and this one equation number 2. Let's add those together. If I add those two together, I get P1 final plus P2 final is equal to, so that's adding this and that, is equal to P1 initial plus P2 initial. That's adding that one to that one. And then I've got force from 2 times delta t plus force from 1 times that same delta t. Now we know, because of our third, let me call this equation number 3, because of the overall momentum principle, the sum of the system momentum and the sum of the system momentum are the same before and after. So these two terms, this term and that term, they have to cancel from both sides of this equation. The momentum has got to be, the momentum of the system cannot change. The individual momentum of object number 1, that does not have to be the P1 final, does not have to be P1 initial, but for the system it does. And that leaves us with this statement, that 0 is equal to delta t, I'm going to factor a delta t out, force from 2 plus force from 1. Or, now the delta t doesn't matter. I get the force from 2 is equal to minus the force from 1. And that is the third law of Newton. However, we see it as an application, a special case of the momentum principle when you have an isolated system. So what I'm asking here in this clicker question, when we get to it, I'm asking, is object 1 isolated? Object 1 plus 2 together, they are isolated. That's the statement of the problem. But object 1, you could easily have something like object number 1, object number 2. There's the initial state, the final state, stuck together. Crunch. This guy's momentum changed. If you were in that car that crashed, you would feel that change in momentum. If you were there, you would feel that change in momentum. But the overall system momentum did not change. And it allows us to conclude this incredible statement that the sizes of the interactions are exactly the same and point in opposite directions. And we'll use that lots to analyze different situations.